You know, it feels like multi-core microcontrollers are popping up just about everywhere these days. They're letting us tackle some really complex jobs, like machine learning or just managing a Wi-Fi stack without breaking a sweat. But here's the thing, how do you manage two brains without causing total chaos? Today, we're going to dive into one of the most popular dual-core chips out there, the ESP-32, to figure that out.
And it's a fair question, right? For the longest time, one core was more than enough. But as our little embedded devices get smarter and way more connected, the demands on that single processor have just gone through the roof. So why exactly do they need to double up? What's the big deal?
Well, think about it like this. You can have one core totally dedicated to managing those super time-sensitive things, like the Wi-Fi and Bluetooth stacks, making sure you never ever miss a data packet. And that leaves the other core completely free to run your main application, whether that's crunching sensor data or even running a machine learning model. This separation, this division of labor, is really the secret sauce to building responsive and super reliable devices.
Okay, so to really get how these cores work together, we need to look at the two big models for multiprocessing, asymmetric and symmetric. These are basically the blueprints for how any multi-core system is designed to operate.
So with asymmetric multiprocessing, or AMP, you've got a clear boss, a manager core that hands out jobs to the others. It's a top-down approach. On the other hand, symmetric multiprocessing, or SMP, is more like a partnership. All the cores are equals, they're all running the same operating system, and they just pull tasks from a shared to-do list. And that SMP model, well, that's exactly what the ESP-32 uses, so it's what we're going to focus on.
All right, enough theory. Let's get our hands dirty and ground this in a real-world example that, let's be honest, a lot of you probably have on your desk right now, the ESP-32. We're going to see exactly how it puts that symmetric, dual-core architecture to work.
Okay, so inside the ESP-32, you've got two identical cores, CPU 0 and CPU 1. By convention, CPU 0 is the one handling all the networking stuff, and CPU 1 is free to run your application code. They share memory, but, and this is a really big but, the FreeRTOS operating system that so many of us use doesn't actually support multiple cores out of the box. The magic that makes it all work comes from the ESP-IDF, which is the official software framework for MSPRSIF. And here's the crucial part. It gives each core its own, totally independent scheduler to manage its tasks.
So this brings us to the big dilemma for any multi-core developer. Do you manually assign or pin your tasks to specific cores, or do you just let the schedulers figure it all out? Because making the wrong choice can have, well, let's just say some dramatic consequences. Let me tell you a little story.
So, picture this. You've got a really high-priority task, something you think is so important it needs to run all the time, but you've written it in a way that it just hogs the processor, stuck in a tight loop, never pausing to let anything else, even lower priority stuff, get a word in. What do you think happens next?
Let's just look at this code snippet here. We've got task H with a high priority and task L with a low priority. Now notice that both of them have been explicitly pinned to run on core 0. And task H is written with what's called a busy wait loop, which means it never ever yields control of the processor. It just spins and spins.
So at first, the result is exactly what you'd expect. Task L, the poor low-priority task, is completely starved. It never gets a single chance to run. But then something really weird happens. After a few seconds, the entire system just resets. It reboots itself. Why? What's going on?
Meet the culprit, the watchdog timer. On the ESP-32, Core 0 has this little hardware safety net, and its main job is to protect really essential tasks, like the Wi-Fi stack. If our high-priority task hogs the CPU for too long and the scheduler doesn't get a chance to run, the watchdog just assumes the whole system is frozen up and it hits the big red reset button. It's a safety feature that in our case just completely backfired.
So that little disaster perfectly sets up the developer's dilemma, right? We've basically got two main strategies for assigning tasks, and each one comes with some major trade-offs. It's really a choice between having total control and just the convenience of letting the system handle it for you.
This table kind of breaks it down. Pinning tasks gives you absolute control and really predictable behavior. It can even make things faster by avoiding what are called cache misses, which is when a task has to waste time reloading its data because it switched cores. The downside? Well, now you're the manager. You have to manually balance the load between the cores yourself. On the other hand, you can set no affinity and just let the schedulers decide. It's easy, it's great for CPU utilization, but you lose that critical predictability.
So what's the verdict? For a big desktop PC,
yeah, you'll let the OS handle it. But for a microcontroller, the advice is pretty clear. Pin your tasks. That extra control and predictability you get is almost always worth the extra effort. In fact, the ESP-32 itself agrees. By default, it pins the Wi-Fi and Bluetooth tasks right onto Core 0.
Okay, so now that we've got the basics of task assignment down, let's level up and talk about a more advanced, and frankly, a more dangerous part of multi-core programming: protecting shared resources with something called a spin lock.
So when you have a chunk of code, a critical section, that absolutely cannot be interrupted, you have to protect it with a lock. Now, you might be familiar with a mutex, which basically puts a task to sleep if it tries to access a locked resource. A spin lock is a totally different beast. If a core tries to get a busy spin lock, it doesn't go to sleep. It just spins in a tight loop, actively waiting and burning 100% of its CPU cycles doing nothing until that lock is free.
And this is where things can go so horribly wrong. Check out this scenario. Core 1 grabs a spin lock, and then, for whatever reason, it hits a long delay while it's still holding that lock. Now, Core 0 comes along, and it needs that same lock to do its job. What happens? It gets stuck. It's just spinning, uselessly, wasting its entire processing budget doing absolutely nothing until Core 1 finally finishes. You've effectively just paralyzed an entire core.
So what's the one thing you need to remember here? The crucial point is this. If you have to use critical sections protected by spin locks, you have got to make them fast, like lightning fast. Get in, do what you need to do, and get out as quickly as you possibly can. A long delay inside a critical section is just a recipe for total disaster in a multi-core system.
And that pretty much brings us to the end. We've seen the power and, the pitfalls of multi-core programming. Just remember the key lessons. Always respect that watchdog timer, keep your critical sections super short, and really understand that trade-off between control and convenience. So for your next project, which one are you going to be? The hands-on micromanager pinning every task for maximum control, or the delegator trusting the scheduler to do all the heavy lifting? The choice is yours. Thanks for tuning in.